to start thinking about sources of errors not being mistakes. Everything you can avoid is not a source of error. An error is something that is there. An error is something that you know exists on the setup, but you cannot remove it. However, you can reduce it to zero or to a value very close to zero, but you cannot get rid of it, like friction. So rounding is not an error. Calculation mistakes are not errors. Don't say error because of the measuring tool. How about you discuss the limited precision of the measuring tool? Don't say human errors are mistakes, I do. You can think about your slow reaction time while timing something, or while trying to keep a constant velocity through your centripetal force device, platform, and so on. So try to discuss things having limited precision, or when you say your platform is supposed to be horizontal, but it cannot be perfectly horizontal, you see? So don't think about them being mistakes, or don't simply say, I have an error here, here, and there. It's due to what? That's the question, okay? Anybody would like to speak up concerning midterm or some related? Yes, who's raising hand? Tell me.
Nida.
Yes, Maria. Yes.
Doctor, in the midterm, how will we calculate the slope and the error on it?
All right, so the slope can be done using the simple calculator by simply plugging the value, click regression, click slope. It is faster than Excel. Make sure you learn or you know how to do it. It's faster than Excel because you don't need to plot. Okay, this is one. The error on the slope, however, needs a lot of time, and we will try our best not to give you error on the slope. If we ever give you error on the slope, know for a fact that it will be easy for you to pick or choose from the answers given to you without any calculation. We don't want any time-consuming calculation, okay? Do you want us to send the scratch after the exam? No, Ali. It's gonna be multiple choice for sure. You pick your answers, you submit, and probably Blackboard is gonna submit for you whenever the time finishes. So yeah, which means you have to manage your time well. Okay, so no scratch needed. Who's raising hand again? Yeah, I think, Carl, it's going to be 20 questions. Probably I can confirm later. Yeah, but around 20 questions. And the timing, I don't know yet. I need to solve the exam slowly and surely and time you later. But I would say 20 questions, around 40 minutes, something like that. And multiple choice only. Anything else you want to know? The questions would cover multiple choice. Would cover data analysis. You will be given questions like, you have a list of values, you need to find the average and the RMS. And again, a lot of questions can be answered without doing any calculation. You can look at the answers first and probably pick or remove the wrong questions, the wrong answers, okay? Sometimes you can answer without doing the full calculation. A lot of questions will be conceptual as well. For example, discussing a qualitative approach of a certain problem. What happens if you double the velocity, the initial velocity in projectile motion? What happens to the range, and so on? You know what I mean by conceptual question? It's a descriptive approach and not something to calculate like any problem in the course, you see? More questions related to the midterm? And yes, you can ask me later. Will it be easy? I don't know, Rita. We did not start writing it. We are busy now correcting your work and writing feedbacks for you. Probably we're gonna write it over the weekend, so I have no idea. We're not planning to torture you. Okay, that's for sure. We just want you to have a rehearsal for the final exam. It's just a mini final exam. We don't want you to go for the final exam as a first trial. You see? What happens in physics? What happened in physics 301? You had issues, yeah? Physics 301 is hard in general, the course. And you had a makeup exam, oh my God. So like extra exams to handle. So do we need to study? Yeah. By the way, Carl, I don't want you to worry. But last year we told Physics 302 not to worry, and a disaster happened. It was not intentional. It's simply that the students found it difficult. So sometimes we don't mean to make it difficult, but for some reason you don't do well. Sometimes you don't finish the exam on time. Usually finishing the exam on time is an issue. And how do we study for the midterm? We're not supposed to study for a midterm because we want to assess skills that you already learned by now, like how to find the slope, how to assess your data, how to analyze your results, and how to understand, like the conceptual understanding. This is something you don't study for. So if you want to study, you can simply go over the labs quickly, go over your lab reports and the mistakes you did quickly, you know, but you're not supposed to study for it. Like, you're supposed to do your lab reports well. You will be given probably questions similar to the assignment you had in lab 0 as well. Okay? But whatever happens, keep in mind that we're here to help. So probably lower the percentage of the midterm and then give you, like, we will give you alternatives later on. Now you have to only think, do your best. Okay? Can we have a formula sheet? I will let you know why not. Because personally, I believe even if I say no to this answer, to this question, you can end up hiding a formula sheet. So since you can hide it, why not give you the permission to have it? Okay, but I need to discuss this with my other colleague. So if I allow you, he has to allow his students as well. How about I write it down so I won't forget? So formula sheet. Question mark. I will let you know. Somebody asked me something about, that's it. Did I answer all your questions? I think I did. All right, so now if you have any question related to lab 4, we can tackle this. By the way, I would love to show you the schedule. I wanted to talk schedule with my other section and I forgot. It is in the syllabus. Let me see. Talk a bit about schedule because you need to know where we are and where we're going before we start lab 6. And if you guys have any question for lab 4, let me know. So back to our schedule. We're done with lab 1, 2, 3, and 5. This week you're gonna go over lab 4. So, and I mean, finish the lab report for lab 4. I'm gonna do lab 6 for this week. Yeah. And after the midterm, we're gonna have 7, 8, 9, and 10. Yesterday, I recorded those. It was nice, it was easy, it was quick. It wasn't perfect though. The recording was not perfect, but it's okay. Like, you know, when you're on the spot and you want to say something and you forget half of it. But we have the pleasure to be in a live session, so I can explain it all, even if I don't explain it well during the videos. Yes, you're going to see the videos anyway. So I assume you have no questions for lab 4 and we can start directly lab 6. Yes? All right. I'm going to take your silence to be positive answer. All right, lab 6, rotational inertia of disk and ring. I know for a fact that you know a lot about rotation since grade 11, since high school, I mean. I know also that in the course you started rotation, but you're not into the dynamics of it and moment of inertia and stuff. So you need a good reminder of your high school material. The experiment is not difficult. However, since we cannot measure the moment of inertia directly, you need to understand how your system is functioning, because you're gonna measure the acceleration of a wire and you're gonna relate the acceleration of the wire that is pulling your system to the moment of inertia, which means you need to know a bit of the physics around the game, you know, and this could be a bit confusing for you. I'm gonna go over each step slowly so you will have a general understanding. A general understanding will help you understand the experiment. Otherwise, the experiment will not be clear to you. But in general, the procedure is so quick and easy, and you will see. The outline that I need to follow is the following: how to understand rotation from translation, because I know that you understand translation very well. You've been doing that since forever. Translation is regular motion in one dimension, for example. So if you can take this from that, probably things are going to be a bit easier. I would want to discuss the moment of inertia of a point system, and then do moment of inertia of any system. It could be 2 points and more. Discuss the setup of the experiment, then discuss the acceleration through the setup, because this is a bit tough, yeah, and then show you the video and discuss the lab report. Okay? Yes. Now, rotation versus translation. I love this chart. So what does it say? Every time you have translation, I'm sorry, I jumped one slide. Okay, I'm just moving a bit. So every time you have translation, you guys do study mass, position, velocity, acceleration, force, and many laws and things. Now, instead of talking about position in meters, we're gonna talk about angular position in rad. This would need, the position needs the x-axis, the angular position would need an angular axis. Velocity in meter per second, now we have angular velocity in rad per second. Acceleration in meter per second squared, and angular acceleration, the unit is, Jana, what's the unit for angular acceleration? Guess? Yes? Jana?
Yes, doctor.
So what's the unit of the angular acceleration?
I'm not sure what it is.
Okay, so the acceleration is meter per second squared, and the angular acceleration is rad per second squared. Excellent. So you guys, for you to move from linear to angular, we usually divide by the radius if we're talking about perfectly circular motion, because this could be applicable to any curve, you know, it doesn't have to have a constant radius. But talking about a circular motion, why not divide by the radius? Now, the idea of mass is very important. You know, mass is inertia, and inertia is laziness, or how heavy the object is for translation. So if I'm gonna move, let's say Carl, and Carl is heavy, he has a big mass, his mass is gonna resist the motion. However, if I need to discuss rotation, the mass alone will not tell me how heavy Carl is. It's also the mass and how far away the distribution is of the mass is around the axis of rotation. And this reminds me of the famous example of the dancer dancing on an ice skating arena. Just imagine Carl doing the dance. When he opens his arms, he is gonna slow down. And whenever he closes his arms, he's gonna go rotate very fast, because the mass, you know, his heavy arms, Carl is heavy, his heavy arms, you know, the mass is going to be distributed away from the center of rotation. So Carl is going to be heavy, he's going to resist the rotation. However, when the mass is distributed close to the rotational axis, the axis of rotation, Carl is going to resist the rotation less and go faster and faster. Carl, do you dance well? Why are you laughing? You don't? Me neither, but I do dance, even though I don't dance well. And it's okay. And you're too lucky we're not in the lab to see me dancing. All right, anyway, now back to our laws. Every time we need to discuss force, force is the one that is gonna push the object to move. For rotation, the force is not enough, because the force can be applied anywhere, and torque is what I need. Torque is the force, it's going to take the force into account, and how far away the force is from the axis of rotation. By the way, torque is not a vector quantity, it's a scalar quantity, and I don't agree with the vector. This is a door, okay? Let me show you. This is a door viewed from above, and this is the axis of rotation. This is how I open the door. It's going to look like this when it's open, you know, open the door, yeah? Now I'm going to undo to remove that. Let's say I'm going to apply the force here, or here, or here. You know, toddlers, babies, they don't know where to push the door. Sometimes they push randomly. In which case, 1, 2, or 3, or 4, do you have a greater rotation? Where you push close to the axis of rotation or farther? Yeah, definitely farther, because what makes rotation is not the force itself, but the torque, and torque is actually related to the force and the lever arm, or the distance away from the leg of the force to the axis of rotation. That's why we actually discuss torque. Now, if I need to jump to this, this is also a repetition. Position and translation, you have angular position and rotation. Displacement, that is actually delta x. We have delta theta, angular displacement. Velocity, angular velocity. Acceleration, angular acceleration. Probably I can ask Rita, what is the unit for angular velocity? Can you guess? What's the unit for velocity? Meter per second, right? So angular velocity will be rad per second, exactly. So simply by dividing by r, I'm removing the meter, and instead of the meter, I have rad per second. Instead of talking about the force, I'm gonna talk about the torque, and I do not agree with this vector. Instead of talking about mass, which is heaviness for inertia, for translation, I need to talk about moment of inertia, which is heaviness for rotation. No, Roy, don't memorize anything. I'm trying to make sense out of this. You can forget it in a moment. By the way, Roy, do you know that kinetic energy is half mv squared, and you have one for rotation? Instead of mass, I'm gonna use moment of inertia, which is how heavy the thing is for rotation. And instead of velocity, I'm gonna use angular velocity, okay? So yes, so you have kinetic energy for an object moving in translation and the kinetic energy for a fan rotating, you know, and the answer is in joules as well. Anyway, now I'm gonna start discussing moment of inertia. So again, what do you understand by moment of inertia? Moment of inertia. Can you explain it using your own terms? Moment of inertia. And let me save as this for your class only, because for each class, it's gonna be a bit different. Yes, moment of inertia. Roy, can you try? What's the difference between the mass of Carl and the moment of inertia of Carl? What's the difference between the mass of Jesse and the moment of inertia of Jesse? Yes, Roy, I'm all ears. Roy Kokajian, because we have two Roys. Unmute yourself and talk. I would want to know what you think. Okay, all right. Anyone would like to add anything to what Roy said? Roy said, how far is it from the center of the axis? Yes, anyone? Maria?
Yes, it's the measure of the resistance of a body to the angular acceleration about a given axis of rotation.
Right. So you actually describe a moment of inertia as being the resistance. Yes, that's great. So instead of discussing the mass itself, yes, the mass is gonna be heavy. It's gonna make my rotation more difficult. It's also where I put the mass, because the closer it is from the axis of rotation, the faster the object can rotate. So to find the moment of inertia I will take the mass and how far away it is from the axis of rotation. So this is the mass, and this is the distance away from the axis of rotation. Okay? Probably ask Romy. Romy, what is the unit for mass? I'm talking SI units.
Kilograms.
Yes. What about the SI unit for R?
Meters.
Yeah, the distance. And what would be the SI unit for I? The moment of inertia.
Kilograms per meter squared.
Yes, definitely. So from now on, Carl, every time you dance, don't think about your kilograms. Think about your kilograms per meter squared, and this is what matters. Now, if I need to go back to Jana, if I need to find the moment of inertia of my system, and my system is made of object 1 and object 2, how do you believe you can find the moment of inertia of the system? Let's say Roy holding 2 books, like 2 systems.
We add the two masses,
yes,
and the distance of each one compared to the center of the axis.
Okay. How about this is?
And is there on both?
Yes, if this is 10 centimeters and this is 20 centimeters. How do you do that?
Do we add them up for the distance?
So you say I do mass 1 plus mass 2, that's total mass, and I do distance 1 plus distance 2, that's total distance. I think this doesn't make sense. I would want you to do I1, then I2.
The difference between them, the difference between the two distances?
No, you're gonna find the moment of inertia of the first system and the moment of inertia of the second system and add them up. Romy, if you wanna do the center of mass, this is also good. Okay, so Romy would say, use total mass, yes, find the position of the center of mass, then take the distance of the center of mass. Why not? Or simply, you are allowed, this is a scalar quantity. You are allowed to do I1, which is I of Carl, and I2, which is I of the book, and add them up like masses. They're scalars, yes, you can add them. So even though the moment of inertia sounds creepy and weird, but eventually you, the behavior of it, like you deal with it the way you deal with a regular mass, okay? So yes, Maria, it's sigma I. Talking of that, let's talk now not about a point system, but a system made of many tiny masses. This is a system made of M1, M2, M3, M4, and M5, each of which is far away from the center of rotation of a distance R1, R2, R3, R4, R5 respectively. To find I of one mass, I do mr squared. And to find I of each, I'm gonna do mi times ri squared. To find the total, I have the right to add them up. Now, talking about add them up, how do you find the moment of inertia of a system that is continuous like a rod? Like you see all this rod, how do you find the moment of inertia of all this rod? Anyone? Yeah? Yes, Kausar, it has a specific eye, but how do you believe the specific eye was found? Do you remember, or do you have a hint, or do you have an idea on how they found the specific eye? So actually they took a tiny piece and they did the moment of inertia of this tiny piece. And then they took this tiny piece and this tiny piece, and then they did I1 plus I2 plus I3 plus I4. But instead of doing sigma m times r squared, they did the integral because it's a continuous addition, okay? And this is how, by the way, they found I of the rod. So they took r squared, which is how far away this tiny object is from the axis of rotation, times a tiny mass, and then they did the integral over all the mass. You see, you don't need to do integrals, don't freak out. I'm just trying to tell you how to deal with the different eyes. So now you can find online or in any textbook eye of a different system that is continuous and homogeneous. For example, rod, it's rotating around the center. This is I for it. And this is a rod rotating around the edge, not the center. And this is I for it. And you see, the position of the axis is very important because it changes the moment of inertia. This is a solid sphere. This is a hoop. This is a disc, a cylinder. This is another table. This is a hollow cylinder. We're gonna use this one because we're dealing with a ring, and a ring is like a very thick bracelet. So this is I because it's gonna rotate around the center, like the axis of rotation. You can see the outer radius, the inner radius. We're gonna take also a plate or a disc. This is called a plate, like your lunch plate, but definitely that's a disc. Again, the title was a moment of inertia of the disc and ring. So we're gonna take these two, okay? You can measure mass, you can measure with a digital measuring tool, measure the radii, inner and outer, with a regular ruler, analog, and the disc as well, and find I theoretical for the ring, I theoretical for the disc, and then do the experiment to find the experimental value. Reminder, there's no means to measure I experimentally. So I is our objective. We're gonna measure something else and then deduce I, okay? And that's the issue. This is our system. Let me explain what you have And let me show you the video as well for you to understand. Okay, this is a disc. Okay, and on top of the disc you have a ring, and the ring is hollow inside. Actually, the disc has like somewhere to put the ring on, like a small opening. Under both, you have wheels. I don't know what how can I describe it, but we call them step pulleys, but they're actually wheels. And what I mean by wheels, do you see this wire? I'm gonna rotate the wire around wheel 1, or around wheel 2, or around wheel 3. For each wheel, it's gonna give me a different torque. Let's say the tension is 2 newtons, as an example. The torque is gonna be related to the radius of the wheel. Let me show you probably. This is the wheel viewed from above. Let me pick a different color. So this is the wheel viewed from the above. And the wire is around this wheels, and then it's gonna pull in this direction. This is the tension T. For the students, all right, so anyway, how do I find torque? Anybody remembers how to calculate torque? No one? So torque is, yes, so the torque is gonna be the cross product between F and R. F is the force applied and R is the lever arm, not really the lever arm, it's the vector that would join the leg of F to the center of rotation. Okay, so it's not regular times, it's a cross product. Anybody remembers what is a cross product? By the way, that's an absolute value because the cross product is a vector as well. Okay, so the cross product will eventually give you a magnitude that is F times R times sine theta. Okay, by the way, physics teachers call this the lever arm, or you can simply take F to be the force, R to be the distance from the leg of the force to the axis of rotation, and theta to be the angle between F and R. This is F, the force applied, and this is R, the distance between the leg of the tension to the axis of rotation, because it's gonna rotate in this direction. Probably I can ask Maria to tell me what is theta in this case. If I'm pulling in this direction and this is R, what is theta in our case? Yes? So the question was again for, I forgot, Maria. Yes, Maria. What is the theta?
The angle between
F and R in our case.
Yeah, F and R. So the tension and the
yes,
radius.
Yes.
So it's 90 degrees?
Yes, it is 90 degrees. And what is sine 90?
1.
Exactly. So that's why Romy said F times R. How do you know? So it's F times R. So she assumed sine theta to be 1, or she simply, I don't know, probably she saw it. Anyway, I'm gonna make sure the wire is perpendicular to the wheel, because I'm gonna pull the wheel to rotate the whole platform. By the way, the platform is gonna be heavy because the disc is heavy and the ring is even heavier. So I need a great force and a big R to be able to create a big torque to rotate the whole platform. This is called a smart pulley. I need to explain very well how it functions. It's a new sensor for us. And this is a hanging weight that will pull all the thing together. So the hanging weight is gonna dictate how heavy how strong my tension is. By the way, the weight is not equal to the tension, but they're related somehow. We're gonna discuss it in a moment. Any questions? So simply I'm gonna pull on the wire by the heavy weight, the hanging weight, to rotate my disc. And if the disc has a big moment of inertia, it's gonna resist the motion and the rotation is gonna be slow. Very easy. Just imagine the disc to be Carl dancing with heavy books in his hands, you know? All right, this is the system again. Theta is not always 90, Roy, but probably I can show you that in this screenshot, that I will try my best to have my pulley aligned in such a way to have 90 degrees between for the wire to be tangent to the wheel. It's gonna be tangent and you will have 90. Just to simplify, otherwise I need to measure theta and it's gonna be a big deal. So for me not to go and measure theta, I'm gonna take theta to be 90. Okay, it's not difficult. Just make sure the wire is aligned to the pulley or the pulley is aligned with the wire as it is, tangent to the wheel. This is again another picture to show you the disc, the ring on top. This is the base. It's inside the ring and you have 3 wheels. We call them 3-stage spools or 3 step pulleys. By the way, they call them in the booklet, in your manual, step pulleys. Step pulleys. I want you to know this because you have step pulleys and you have a smart pulley and you need to know the difference. Okay, so what is a smart pulley? The smart pulley is this. Let me pick a pen. This is a smart pulley, the sensor that is gonna measure the velocity of the whole thing. And the step pulleys are the different wheels I have here of different radius, and that's very important. Okay, so you see the smart pulley here is clamped to the table. In this case, the smart pulley is clamped to my base and it doesn't matter. By the way, this is what I have in the lab and not this one. So this is another picture to make sure you understood the setup. Now, are you ready for the derivations? I need to relate I, which is the moment of inertia of my system, and my system could be the whole thing together, to the acceleration of the hanging mass. So this is acceleration and this is I. How do I relate I to acceleration? My measuring tools will give me acceleration. I need to find I from the acceleration. Anyone has an idea how I can relate this guy to this guy? Would you want to try? How can I relate this to this? Anyone? Do you have a plan? Acceleration is related to the net force and net force is related to tension, and tension is gonna give me a torque and the torque is gonna give me an angular acceleration which is related to the acceleration. That's it. F equals ma, we have F, we replace. Do they have the same tension? Since the wire, good question to start with, since the wire cannot be extended, like it cannot be it's not elastic, the tension everywhere is the same. So yeah, I think I know your plan. Anyone would like to describe the method or a plan? Yeah, but Kausar and Romi, that's a good start. All right, so I'm gonna start describing it with you. Sounds long, but it's not difficult. First of all, let me start by discussing that the theoretical moment of inertia of the ring is given by this. We're gonna write it on our notebooks because we need to find theory, and at the end, we're gonna find the experimental one. The theoretical moment of inertia of a disk is given by this one. And again, I just took them from this table. No, this table. So nothing new. Done with the theory. Now the experiments. I'm gonna start by saying, so again, what do I need? I need I. So I is equal to torque. Okay, where did I get this equation from? Let me start by stating that the net force is equal to ma. Am I right? This is Newton's second law for translation. Newton's second law for rotation is gonna be the same idea. Instead of net force, I'm gonna say net torque is equal to, instead of mass, which is inertia for translation, I'm gonna use moment of inertia. Instead of acceleration meter per second squared, I'm gonna use alpha, yes, which is rad per second squared. The only force applied to my system is the tension. Okay, so I'm gonna find the torque done by the tension. So this is the torque done by the tension. And this is nothing but acceleration over the radius, because the best way to find the angular stuff is to divide by the radius, right? So we're done with this guy. We only need to find the torque, which is force times R. Now let's find the force using Newton's second law. We're done. Okay, so they just said here that the torque, didn't Romy say F times R? Okay, times sine 90. R is R. By the way, be careful. R was here. Where did I draw R? Where is it? R is the radius of the step pulley, or the radius of the wheel that is here. It's not the radius of the disc, neither the radius of the ring. Be careful. It's the radius of the tiny wheel under the platform. Okay? So back to my equation. R is in the torque, and F is basically the tension. That's why they wrote R times tension. Okay? So we just said R times tension. Now let's do Newton's second law to find the tension. I want someone on board. Anyone? Let me pick somebody new from the participants. I would want to talk to Emilio. Emilio, are you there? You're too many and I talk to the same people. I'm so sorry. That's so bad. Emilio?
Yes, I'm here.
Yeah, I'm glad to hear your voice. Okay, Emilio, I'm gonna take this example and I love it because it's a nice diagram. Just a second. Okay, I'm just gonna zoom in. So question number 1 for Emilio is, what are the forces on my hanging weight?
It's T and the weight.
All right, so it's gonna be mg and tension. Okay, do you believe that the hanging weight is in equilibrium?
Yes, it should be.
All right, how about I release the hanging weight? The hanging weight is heavy. It's gonna pull on the wire and the wire is gonna pull on the wheel and the wheel is gonna start rotating. I know the disc and ring are heavy, but eventually a good torque will rotate the whole thing and the hanging mass is gonna fall down to hit the floor if the wire is long enough. So now tell me, is the hanging weight in equilibrium?
No, it's not.
It's gonna speed up and you're gonna have an acceleration that is not as big as the free fall acceleration. It's gonna be so small and so slow, but it's gonna speed up even if it's slow, all right? So I'm gonna use net force equals to ma. So the acceleration is downward or upward?
It's downward.
Okay, this is how I need a pen that can be, I know this blue color is limiting me. So shall I write? So I need to write something for net force. Do I write T minus mg or mg minus T? If I follow A to be my positive direction.
Mg minus T.
Awesome. Mg minus T is equal to ma. I'm sorry for the color. Yes, and how would you find T?
T equals M A minus G.
No. Do it again.
Sorry, Mg minus A, yes.
Yeah. By the way, I asked the same question for the 3 sections and the 3 sections gave me your answer, which is wrong. So it's okay. So apparently you guys do the same mistake. So this is it. Tension is mg minus A, mg minus ma. You see? So back to our equation. This was our main equation. I'm gonna replace alpha by acceleration over radius. I will replace torque by tension times R, and the tension is mg minus ma given by Emilio. Thank you, Emilio, so much. So back again to this equation. I is torque over alpha. This is the torque. It's R times tension, and the tension is mg minus ma. I'm trying to zoom in. Scrolling is a bit difficult because I'm recording the session. It is a bit slow. Okay, then I'm gonna divide by alpha, which is 80 over R. And yes, you guessed right, there's a typo mistake. This is divided. Okay, divided by a fraction is like multiplying by the inverse. And then you can expand and you will end up with this. And this is actually awesome because this is I equals to this. You can find the acceleration of your system by a regular sensor. It could be a motion sensor. It could be a smart pulley. And by finding the acceleration, G is known to be 9.81. I know this is an assumption, but it's not a bad assumption. R is the radius of the step pulley, which is the wheel under my platform, and it's usually around 2 centimeters. And this is the hanging mass Emilio was doing Newton's law for. and not the mass of the ring, neither the mass of the disk. And knowing that, you can deduce I of any system that is on top of my platform. Okay, so I is measured indirectly by finding A. The smart pulley is gonna give me a VT graph. So a VT graph, it's gonna be linear because you're gonna see a constant acceleration. When you release the hanging mass, it's gonna start slow, then speed up, speed up, speed up in a linear way. And by finding the slope, this is gonna be your A. So your job is to release the system, click start, stop, find the slope. The system is gonna give you the slope, the app, the application. So your job is to do nothing, just release the hanging weight. It's gonna give you 8. You're gonna repeat it 10 times for the ring, for the disc, and then 10 times for the ring and the disc together, because you cannot put the ring alone on the platform. That's it, the experiment is over. Now, Kausar is asking, can we automatically use the formula and we have to show you how we got it? Good question. I can see you're worried. I can feel you. No, you're not supposed to know the derivations at all. You can forget about them. I just want you to understand them by following me, because understanding this will help you understand the whole experiment. But no, you don't need the derivation. Eventually, you're going to erase it all and you're going to say I is mr squared g over at minus 1. And believe me, I did that. I didn't know the derivation. I had to learn the derivations to tell you about them, because I believe this would help you understand the experiment. Back in the old days, I used to do the experiment blindly, find A, find I, and that's it. But going through the steps is important, because you would know that the wire should be aligned, the pulley should be aligned with the wire. I want 90 degrees. You would see the acceleration and understand why. You would understand what happens if I have a heavier hanging mass. If I have a heavier hanging mass, I know for a fact that I is a constant, because I of my disc and ring is not going to change. So changing M is going to change my acceleration. But this doesn't say that disc and ring or car dancing is going to be less heavy or less resisting the motion, and so on. So, Kausar, I believe this is important for the understanding of the setup itself. But no, you can forget this, and nobody is going to ask you about it. Okay? But my duty is to show you why I cannot measure I and how I can measure it indirectly. Okay? Now the setup, these are screenshots of the video, and I'm gonna show you the video. So this is the disc. It's actually heavy, and you see this. It's basically, I'm sorry. Yes, this is an opening to put the ring on. So if I'm assuming the disk to be homogeneous, that's a source of error, because by stating half mr squared to be I, I'm assuming it's a flat disk, and it's not. And here I'm putting the ring on top of the disk. This is the smart pulley. I still need to explain how it functions. It's a regular pulley with a photogate, actually. And the photogate is gonna help me find V, the velocity of my pulley, the linear velocity of my pulley. Here I'm trying to rotate the wire around the wheel. And what I have here is a VT graph, and you see the linear behavior. And it's gonna, you see Emilio, it's gonna hit the floor. That's why I have this weird behavior eventually, but I'm gonna ignore it. So just focus on the part where the speed is increasing in a linear way to find the slope. All right, now videos, I have those videos. Which one comes first? This one. Yes, so we took this video 2 Mondays ago. Here I'm showing you the setup. This is the disc. It's heavy. I will put the disc, you know, it has an opened, it has a hole inside, so it will go through the platform. It's gonna lock, so you cannot rotate it unless the whole platform rotates. So it's locked. It's rotating, friction is very low, it's not gonna stop, it will take forever to stop. So yeah, and you see the hanging weight, by the way, it's going up and down, because when I rotate the platform, the wire is gonna rotate around the wheel and it's gonna get shorter. By the way, this hanging weight is very, very small. It's not gonna move my system, heavy system. So I will add more masses to my hanging weight. Okay, and here I'm gonna show you the wire a bit. Add the ring on top just to play around with the system to see how it functions. Remove the ring. Yes. remove the disc and look well to the wheels, and you will see the wire. It's very thin though. I don't know if you can see it. This is the hanging weight. Yeah, it's very light, probably 10 grams. Plus the blue is 5, so 15 grams. I'm gonna add to this. And you see now the step pulleys. So those, you call them step pulleys, okay? Okay, so you can see, okay, this is the Photogate. I will explain how it functions. And by the way, do you see the wire is not aligned with the pulley? I'm gonna align it in a moment. Okay, turn it left and right a bit. Okay, it could be a source of error. Here I'm explaining that I have 3 wheels of different radii. I will pick the biggest wheel and rotate the wire around it to create the biggest torque available. You see R and wire 90 degrees. I hope so. Yes, but it's gonna be 90 anyway because it's tangent. All right, so the wire around the pulley, explaining slowly how things are, because I need you to understand. And this is going to the floor, by the way. The floor, the chairs are removed on purpose because we don't want any obstacle. Okay, so yeah, that's the end of the first video. I'm gonna stitch them together for sure. And then here, what do I have? I'm explaining how the Photogate functions. This is very important. Listen up. It's a new sensor. It sends a beam between these 2 terminals. The beam is electromagnetic, if I'm not wrong. Yes, it is. Like any remote control, let's say infrared. The beam is gonna go from here to here. If I block the beam with my finger, it's gonna register the time through the block. And you know the pulley has some empty slots and some black slots, right? So the beam is gonna go inside the empty slots, and then the black slots will block the beam through a certain time. The dimensions of the pulley are already in our app, Data Studio, which means they know the radius of the pulley. They know how thick the black slots are. So by simply knowing the time of the block, they can tell how fast, speed equals distance over time, how fast the pulley is rotating. I mean by fast linear speed, or basically angular speed times the radius. And it can tell easily, if you know the linear speed of the pulley, you know the linear speed of the wire, and which is the same linear speed of the hanging weight, because nothing is slipping, they're turning all together. So I'm showing you now how the Photogate functions, how the beam goes from the 2 sides. You see, you're gonna see a tiny light in here to show you every time I block the beam, this light is gonna go on, like a regular remote control. Now, I don't know, now new remote controls, they don't have this. Old lady me used to have this in the past. Now with your Apple TV, I don't know, it's different. So yes, I'm blocking the beam with my finger, and then with the pulley, probably let me play this a bit. Pulley. Every time the pulley is rotating, it can measure the time through which the beam has been blocked. Knowing the sizes of the black plastic beams of the pulley, it can tell the speed. So the time through... Yes, so basically this is what I wanted you to see. All right. All right, so now Data Studio, as a function of time. Yeah, so Data Studio is gonna give you V versus T, and you see a beautiful line, and then randomness. Randomness due to the collision with the floor, due to the fact that the wire will finish and it's gonna stop your system at some point. Any obstacle, so it doesn't matter. I want us to focus on the linear part. That's why I highlighted the linear part in yellow. I'm gonna highlight the part I want the slope of. So Data Studio will give me the slope of only this part. I'm gonna continue, yeah. I'll probably show you the experiment. I will put the disc. Now I'm rotating the wire along the biggest radius wheel. Okay, slowly. I will release. I will delete this. I will delete all the runs. I will approach the mouse. I will click on record as soon as I release my system. Okay. As I can see that my system is starting very, very slow. It is very slow because the hanging weight is so light. And remember, this is so heavy. It's like Carl with open arms, you know? I would love to see Carl. بيطلع Carl ضعيف. I'm sorry, Carl. So Could be that the hanging weight is actually very, very small. I will repeat the experiment with a bigger hanging weight, but let me see, probably this would be good enough. I can see some acceleration, but it's still very small. So it is speeding up. Okay, I will stop recording. All right, let me see if I can zoom in a bit to show you. So you see how small the slope is? Slope is acceleration, and the acceleration is so small. But if you zoom in, you will be fine. Look, I zoomed in, I found a super line, highlighted, found the slope. I know a very tiny slope means the system is very slow, and probably friction is not gonna be neglected. So the slower the system, the more errors probably you will have. Okay, so that's why I decided, by the way, you see how I was selecting only the part that is linear. Okay, so the thing is, I want us to repeat the experiment with a heavier weight. So I'm rotating the wire again, and I think repetition is good for you to see that I'm repeating the same exact procedure and eventually get a graph that looks much better. You see the slope is higher. I will zoom in a key for you to see the slope well, and I will select only the linear part. And yeah, find the slope, and so on. Oh, by the way, I did the experiment with the disk, and then disk and ring together because I cannot put the ring alone. It doesn't have a platform to sit. Now let me show you the lab report. The lab report looks like this, okay? Step Pulley radius, I'm gonna give it to you. You should guess the uncertainty. I measured it with a regular ruler. Ring inner outer measured with a regular ruler of the ring. Disk radius measured with a regular ruler. Mass and mass measured with a regular, with a digital balance. And it will be given to you. Theoretical values for I disk and I ring, you already have the values for the theoretical and the theoretical. Okay? So your job is to find it with the error. So to find the error, you do the propagation of error. It looks difficult, but it's not because the derivative is easy. Then I will give you the following. I will do the experiment 10 times, 10 trials of the same exact procedure repeated 10 times, where I release my system, find the slope, which is 80, ring and disk together, then do disk alone. 80 will give me I, right? So by finding I of ring and disk for the first one, and then find I of the disk for the second one. So this is experimental and this is experimental. And I mean by experimental from the experimental acceleration. Now my question could be for somebody I did not talk to today, and it could be Chloe. Chloe, I can ask you a very simple question, and if you don't know, you can simply say, I don't know, no pressure. Chloe, are you there?
Yes, doctor.
Okay, Chloe, my question for you is, if I find the moment of inertia of the disk, and I find the moment of inertia of the system ring plus disk, how do I find the moment of inertia of the ring alone? I cannot do the experiment with the ring. How can I find it from these two values?
Can I subtract
Exactly.
Well of done. The ring and the disk minus the inertia of the disk?
Yes, since we already said that I of the system is I1 plus I2, and we can handle I like M, we can add I's easily. So yes, to find the one for the ring, I can minus the disk out. Awesome. So that's it. And then you will be given a table where you can summarize all your values like I disk theoretical and I ring theoretical, I disk experimental, I ring experimental, do the percentage difference and do all the analysis. And this is, by the way, a picture to show you the VT graph, the linear part. So this is V, this is T, and the slope. That would be, what is the slope in the VT graph? Anyone? Probably I can talk to somebody I did not talk to, and the somebody could be Diana. Diana, are you there? Yes, Diana, can I hear you? Yes, so the question is for you. In this VT graph, what does the slope represent? Can you remind me? Yes, it is the acceleration, which is AT. And why do I measure AT? What's my purpose? You can say, I don't know. It's okay. All right, I'm gonna ask Kausar. Kausar, when I find AT experimentally from the slope, why am I doing this? To get experimental inertia. Okay, how do I get experimental inertia from the acceleration? Anyone? Anyone can write on the chat. How can I find this from this? From the formula. Which formula? This big formula. Like to find I is equal to that, okay? So Diana, keep that in mind because I know it's a bit confusing. So we find AT from the slope, and using AT I can find I. I is the question mark. Where's my pointer? It's here. I is the question mark, and that's my main objective. Okay, so that's it for this experiment. You will see it's not gonna be difficult because you don't have a plot to do. You just need to do the average RMS and then deduce I. Probably you have a lot of propagation of error, and it's okay. It's good practice for you. I'm gonna save it, send it to you. I will stop recording, and I'm gonna